Welcome to the lecture solving problems section of chapter 5. This is part 1. Let's begin with the first question. Why do you lunge forward when your car suddenly comes to a stop? Why do you feel you're pressed backward against the seat when your car rapidly accelerates? This question refers to Newton's first law, which is also known as the law of inertia. And inertia, if you recall, is the property that objects have toward maintaining their state of motion. So, for example, if you are moving forward with the car at, say, the speed of the car, and you suddenly apply the brakes, your inertia wants to keep you moving at the speed that the car was moving at before the brakes were applied. When you apply the brakes, you're stopping the car, and if you're not attached to the car, you continue to move in the forward direction at the same speed. The opposite is true if you quickly accelerate the car from a start. So your inertia tells you that you are in a state of rest. And as you quickly apply the accelerator, the car moves forward, and so the car seat presses on your back to take you forward along, since you want to stay at your present state of motion. Second question. A space explorer in a spaceship is moving through space. She notices a large rock, and this rock is floating around the cabin of the spaceship. Should she push it gently toward a storage compartment, or should she kick it hard towards the compartment? This is a Newton's second law problem. In it, we know that if a force is applied to a mass, the mass will accelerate. If she applies a large force, because the mass is relatively large, the acceleration on the boulder will be relatively small. However, by the third law, we know that the force will be equal in magnitude toward her, but in the opposite direction. So in other words, if she applies a large force will be applied to her. Because her mass is relatively small, she will experience a greater acceleration than the rock. So the answer to this question is she should push it gently toward the storage compartment. Question 3. Why does a sled that is pulled by a horse accelerate? The answer is given in red here. The horse exerts a force on the sled. The sled, however, exerts a force of equal magnitude on the horse. But the forces don't cancel since they act on two different objects. And as you can see here, where we have the sled experiences a force of tension to the right, the horse experiences a force of tension to the left. The sled, however, still accelerates because it has a force of tension to the right and some friction to slow it down to the left. But if you notice the length of the arrows, T is a longer arrow than F for the sled, so the sled has a net forward acceleration. In the case of the horse, we see that the horse is pulled back by the tension on the rope, but since the horse pushes back with his feet on the road exerts a force of static friction that thrusts the horse forward, and you can see by the lengths of the arrows there will be a net forward acceleration on the horse, or a net force on the horse that is to the right, and so the horse is able to accelerate as well. Question 4 says 3 blocks are in contact with each other on a frictionless horizontal surface. There is a force of 18 newtons applied to the system of the blocks, where M1 is 2 kilograms, M2 is 3 kilograms, and M3 is 4 kilograms. We are asked to draw a free body diagram of each block and find the resultant force on each block. But first, let's view a video animation of this situation.
The contact force exerted by the hand on block 1 results in the acceleration of both blocks 1 and 2. If the acceleration of the system is A, then the force exerted must be M1 plus M2 times A. By Newton's third law, block 1 must push back against the hand with an equal and opposite force. It is the contact force of block 1 on block 2 that accelerates block 2. Because block 2's acceleration is A, this force must be M2 times A. Again, by Newton's third law, block 2 must apply an equal and opposite force on block 1.
Okay, so you can see that although the system of blocks has a common acceleration, there are forces, individual forces applied on each of the blocks. So let's first set out to determine the acceleration of each of the blocks, M1 plus M2 plus M3 times A. Okay, so let's see. Let's extend the page here. We've got the acceleration is going to be equal to 18 newtons, which is the value of F, divided by 2 plus 3 plus 4, which is 9 kilograms. And that gives us an acceleration of 2 meters per second squared for each of the blocks. Okay, so now let's go ahead and individually draw the forces on each of the blocks. Let's start with block 1. We've got F applied directly onto block 1. We've got gravity, M1G. We've got the normal force, N. Let's label this F. And then we have the force that block 2 exerts on block 1. We'll call that N21. The block 2, the normal force exerted by block 2 on block 1. And you can see that because there is no acceleration in the y direction, in other words, the block is not losing contact with the surface, then that just means that the normal force that the table or the surface exerts on the block is just equal to its weight. However, you can see that there are forces in the horizontal, and these, in fact, the net of these is what is responsible for the block's acceleration. And you can see here that these forces are F for 18 newtons minus N21, yet to be determined. And that is equal to 2 kilograms, which is the mass of block 1, times 2 meters per second squared. And that tells us that the net force on block 1 is 4 newtons. Since we know that F is 18 newtons you can see that N21, if we solve for this, put it on the other side, is 18 minus 4, which is 12 newtons. However, the net force, which is what we were asked to determine, is 4 newtons. Now let's consider block 2. For block 2, we have the contact force from block 1 on 2. We call that N12. We have the contact force from block 3. We call that N32, the block 3 on block 2. Of course, we've got M2G, the force of gravity on the block, and N, the normal force on the block. Here again, AY is equal to 0. So we know the normal force is equal to M2G, but in the horizontal direction, we've got N12 minus N32 equals M2 times the acceleration. M2 was given as 3 kilograms. The acceleration we know is 2 meters per second squared. And so we have a net force of 6 newtons. Now, since N21 and N12 are both of the same magnitude, we know N12 is 12 newtons. And if we wanted to solve for N32, we know N32 is 12 newtons minus 6 newtons, or 6 newtons. So here we've got the net force on block 2. Sorry, this number is incorrect. Apologize. This is 14 newtons. 18 minus 4 is 14. And so this number here is 8 newtons. Sorry about that. Okay, now let's go ahead and look at block 3. Block 3 has a force N32, the force that block 2 exerts on block 3. It's got the weight, M3G, a normal force, and no other force in the horizontal. But of course, again, AY equals 0, so we know N equals M3G, and N32 is equal to M3 times A. M3 is 4 kilograms. A is 2 meters per second squared. That gives us 8 newtons. And so we know N32 is 8 newtons, and so is N23. And actually, that should have been 23 by block 3 on block 2. So we now have the net force on each of the blocks and the free body diagram on each. Okay, question 5. Two forces F1 and F2 act on an object which is 5 kilograms, and we're told to ignore gravity. The magnitudes of the forces are F1 is 20 newtons, F2 is 15 newtons. The question is, find the accelerations of the mass in case A and in case B. Well, here we have to consider the vector nature of forces and add these forces as vectors. So let's consider the case A. Here we know F1 is entirely along the x direction, so we know that F1 is 20 I hat newtons. F2 is entirely along the y direction, 15 J hat newtons. And so from here, you can see that the net force on the mass is equal to 20 I hat plus 15 J hat newtons. And so A is equal to the net force divided by the mass, and that should give us 4 I hat plus 3 J hat, and the unit will be the meters per second squared. Now in B, we have a slightly different situation because now F2 has components. So while F1 is still entirely, in the I hat direction, we have to consider that F2 has both X and Y components, and F2 is going to be, let's see if we can draw it here. Here's F2Y, here's F2X, F2X is equal to F2 times the sine of 30 degrees, right? Because this is a 30-degree angle, and F2X is the side opposite the angle, and F2Y is given by F2 cosine of 30 degrees, since this is the side which is adjacent to the angle. So as a result, for F2, we get the components equal to 27.5. Oops, we've changed color. 27.5 I hat. Oh, excuse me, that's not so. It's 7. Let's erase this. Okay. Uh, 7.5 newtons in the I hat direction plus 13 newtons in the J hat direction. That's better. So now we want to add the net force on the mass, 27.5 I hat plus 13 J hat with the unit of Newton, and the acceleration will be the net force divided by m, and that should give us 5.5 I hat plus 2.6 J hat meters per second squared. Next question. Here, a car is given to us on an icy inclined driveway. We are to assume that there is no friction, and we are asked to determine the acceleration of the car. And by the way, that angle that is shown as Q is not Q, it's angle theta. Something has happened to our Greek. So notice that the diagram has given us a, right here, we've been given a free body diagram, but let's see if we can't do a little bit better than that ourselves. Let's draw an incline. This is the X direction. Oops. Something happened to our ink. Oops. And perpendicular to that is Y. Oops. Keep losing our ink. here is our car, and the forces on the car, let's see, we got a normal force. We've got the force of gravity, which is straight downward. We've got a component of the force of gravity, mg, that is adjacent to the angle, where the angle theta is right here. And then we have mg sine theta, which is the side that is opposite the angle. Okay? And there's no friction, so basically we only have two forces acting on the car. That is the normal force and mg. We are going to, because we have taken the components of mg that are both parallel and perpendicular to the incline, we no longer want to work with mg, but rather mg cosine theta and mg sine theta. Now we know that this car is not accelerating in either the x direction, in the y direction. And so basically that just tells us that the normal force is equal to the component of gravity that is perpendicular to the incline. In other words, the normal force is given by mg cosine theta. On the other hand, we have a car that is accelerating along the incline, and so here, the incline being the x direction, we have a component of gravity, mg sine theta, which is not balanced by any other forces, and so we can see that the m's cancel out, and therefore the acceleration along the incline is given by g times the sine of theta, whatever the angle theta would be. So the bigger the angle theta, the greater the value of sine of theta will be, and the closer the value of the acceleration will be to g, which is 9.8 meters per second squared. Okay, last question in part 1. A woman is towing her 20-kilogram suitcase at constant speed. Very important that we notice that constant speed here implies the acceleration along the ground is 0, and if the suitcase maintains contact with the ground, it will also be true that there is no vertical acceleration. Okay, so she pulls on the strap, making an angle theta above the horizontal. The force that she exerts, the pulling force, is given by 35 newtons, and the frictional force, which is the friction that the ground exerts on the suitcase at ground level, is given by 20 newtons. The question is, what angle does the strap make with the horizontal, and what is the normal force that the ground exerts on the suitcase? So essentially, we have two unknowns, and to solve for these, we will need, of course, two equations. But the first thing we want to do is to draw a free body diagram showing all the forces that are acting on the suitcase. We have the force of gravity mg, we've got normal force N, we've got the pulling force P along with its components px, py, let's go ahead and label this py, px, and we have friction, kinetic friction. So these are all of the forces that are acting on the suitcase, and now we have to impose the condition for equilibrium, that both in x and in y there is no acceleration. Well, let's see all the components or forces that may be acting along the x direction. Well, once we have the components of the pulling force in x and y, we don't need to have P labeled there. So we've got Px minus Fk, Fk is equal to 0. There are no other components along the x direction. Px, if we allow this to be the angle theta, can be written as P cosine theta, because it is the side that's adjacent to the angle. And the form of Fk is mu k times n equals 0. Now remember that we are solving for both theta and n, the normal force. So here's our first equation that contains the two unknowns, and we need a second equation to deliver the remaining quantities. And of course, that's going to come from, let's just extend the page, the sum of the forces in the y direction, which are n minus mg plus py. So we have three components along y. N equals mg minus p sine theta. So if we now make a substitution here, you can see that we've got, we can enter the value of n here, eliminate one of the unknowns, and so once one of the unknowns is eliminated, we solve for the other unknown, and thereby, the Fk was given to us. Let me come back up here. We didn't actually need to break it up. This is Fk, which is given to us as 20 newtons. So in fact, we can immediately solve for P, or rather theta, where cosine theta equals Fk over P. And so theta is equal to the inverse cosine of Fk, which is 20 newtons, divided by P, which was given to us as 35 newtons. And this gives us an angle theta, which is 55.2 degrees. Now we come over here and equals mg minus P sine of 55.2 degrees, and this gives us a value of n, which is 167 newtons. Well, this concludes the first part of the lecture problems for Chapter 5. Until next time.